Hey everyone, and welcome to your PPL Exam Prep Explainer. Look, if you're gearing up for that private pilot ground test, you already know there's just a mountain of material. So we're skipping the fluff today. We're jumping straight into mastering the core physics you absolutely need to ace the aerodynamics portion of that exam.
Okay, let's just glance at the syllabus real quick. We're covering the 4 fundamental forces, breaking down the types of drag that are guaranteed to pop up on your test, finding that elusive lift-to-drag sweet spot, and wrapping up with how you actually control it all. Let's get you test ready.
All right, Section 1, the 4 forces in flight. Think of these as the warring factions of aerodynamics. You really have to master these the second you slide into the left seat. First up, we've got thrust. Simply put, thrust is your forward pull. It's that mechanical muscle from your power plant and propeller, and it's constantly fighting against the air that's trying its hardest to hold your aircraft back.
And directly opposing that thrust, that's drag. You see, whenever you shove a physical object through the air, you disrupt the airflow. And that disruption creates a rearward retarding force acting perfectly parallel to your relative wind.
Next up is weight. Basically, it's gravity's relentless downward pull on everything in your aircraft. That's the airframe, you, your passengers, your bags, the fuel, the whole shebang. It always pulls vertically downward, right through the aircraft's exact center of gravity. Which brings us to the actual magic of flight, lift. Lift is what directly opposes that downward weight. It's the upward force keeping us in the sky, generated entirely by the dynamic effect of air rushing over and under your wings. Now here's a really interesting concept that the FAA and your examiners absolutely love to test you on: steady, unaccelerated flight. When you're flying straight and level at a constant speed, you aren't just magically floating. You're actually in a state of perfectly balanced physical tension. It's Newton's third law in action. Opposing forces completely cancel each other out, so the sum of all your upward forces perfectly equals all your downward forces, just like your total forward thrust perfectly equals your total backward drag.
Moving right along to Section 2, we're unpacking Parasite and Induced Drag. This is a massive topic on the exam.
You absolutely have to nail the difference between these two main categories of drag. Parasite drag? It's exactly what it sounds like. It just slows you down and does nothing to help you fly. It's strictly about the physical object moving through the air. Induced drag, though, is the unavoidable penalty of flying. It's literally inseparable from lift. You can't generate lift without simultaneously creating induced drag. It's a package deal. Okay, the crucial thing to remember here is that parasite drag actually breaks down into 3 specific subtypes. First, form drag. This is all about your aircraft's shape. Think bulky engine cowlings or antennas. Second is interference drag. This happens when airflow from 2 different surfaces collides. Like right where your wing meets the fuselage at a 90-degree angle, it creates these swirling, turbulent eddy currents. And finally, skin friction drag. Honestly, no matter how sleek your plane looks, on a microscopic level, it's rougher than a cheap hotel towel. It catches air molecules and drags you down. Seriously, burn this relationship into your memory for the exam, because parasite drag is all about physical resistance. If you speed up, parasite drag shoots up exponentially. You're basically ramming into more air molecules faster. But induced drag does the exact opposite. As you fly faster, your wing gets more efficient at slicing the air at a lower angle of attack, so induced drag drops off. Bottom line, speed up, parasite goes up, induced goes down. Slow down, parasite drops, but induced skyrockets.
And that inverse relationship takes us perfectly into Section 3, the lift-to-drag ratio, finding the sweet spot.
Since parasite drag climbs when you speed up and induced drag climbs when you slow down, there's this one magical intersection point where your total combined drag is at its absolute lowest. We call that LD max. It requires a very specific angle of attack. When you hit this precise spot, you get the absolute maximum amount of lift for the minimum amount of drag. It is literally peak aerodynamic efficiency.
Let's do a quick mental check, because this is a classic exam scenario. They're going to ask you, what happens if you drift away from this perfect LD max angle? You know, what if you pitch up a little bit or pitch down? The answer? Your total drag increases. Always. Any deviation whatsoever from LD max instantly reduces your lift-to-drag ratio. You're operating less efficiently. And that means you're burning more fuel and cutting into your maximum glide distance.
So we know the forces, and we know the drag penalties. Let's look at Section 4, pilot control. How do you actually juggle all this from the cockpit? It's all a balancing act between lift and airspeed.
Lift is proportional to the square of your velocity, meaning if you pull that throttle back and slow down, your wings are suddenly producing way less lift. To stay level and keep from descending, you literally must pitch up and increase that angle of attack. On the flip side, if you push the throttle in and speed up, your wings generate excess lift. If you don't want to start climbing, you have to decrease your angle of attack. You are constantly trading speed against the angle of your wing.
Okay, here's another highly likely exam scenario testing this exact thing. Imagine you're on final approach. You want to touch down as slowly and safely as possible without stalling the airplane. What's your input? What do you actually do to the lift?
Well, because your velocity is dropping, you've got to compensate by squeezing every last drop of lift out of that wing. You have to increase your angle of attack to near maximum. You're balancing that exceptionally slow speed with just enough aerodynamic lift to perfectly match the weight of your aircraft, right up until the rubber meets the runway.
But wait, don't forget the environment. Your wing needs air molecules to create lift, right? Well, high altitudes, hot summer days, and high humidity all do the exact same thing. They lower air density. There are literally fewer air molecules for your wings to grab onto. So, what's your move as the pilot? You have to fly at a greater true airspeed just to get the same amount of lift you'd get on a nice, cold, dry day at sea level. Ultimately, nature sets the baseline. You might be the one holding the yoke, but it's the invisible air density dictating the physical rules of your flight. Your whole job is to masterfully balance thrust, drag, weight, and lift against whatever the environment throws your way. So, next time you hit some sudden turbulence, ask yourself, which of those four forces just shifted, and exactly how are you going to balance it back? Command those elements, and you are going to do great. Hey, if this explainer helped you study, please hit that like button, subscribe to the channel for more PPL prep, and best of luck on your ground test.